So measuring delta E for chemical reactions. And this has to do with the experiment we're going to do on Wednesday. So the system can exchange energy with its surroundings. It can do that through heat or through work. We've talked about both of these now. Heat, Q, is mc delta T, and work, W, is negative external pressure times change in volume. And the change in energy is the sum of those two. So delta E is equal to Q plus W. Well, that gets kind of messy. There's a lot of things to measure to do that. So we can look for simplifying situations. If there's no change in volume, then W is equal to 0, right? Because W is equal to negative external pressure times the change in volume. If the change in volume goes to 0, then W goes to 0 also. And then we don't have to worry about it. So at constant volume, delta E for this reaction is equal to Q. And here we're calling QV, meaning this is the heat at constant volume. And Q is equal to mc delta T. So we're often looking at, well, how much energy is absorbed or released, how much heat from this chemical reaction? But we can't measure the temperature changes of individual chemicals because they're all mixed together, right? So what we do is we measure the change in temperature of the surroundings. And one way to do this is using a bomb calorimeter. A bomb calorimeter is insulated and gives us very controlled surroundings. And so the Q for the system is equal to negative Q for the surroundings. Heat lost by the system is gained by the surroundings. The sign is opposite. And here we can make the calorimeter be the surroundings. It's well insulated, and so we don't have to consider the rest of the universe. Calorimetry is a technique where we measure calories, right? So we measure heat. And we do that by observing changes in temperatures of the surroundings. So we can't directly measure what we're interested in, but we can measure the effect it has on the surroundings. So we have the system, our chemical reaction, and that's going to exchange heat with the surroundings. We can observe the change in the surroundings as a change in temperature. So here's a bomb calorimeter illustration. So this is the bomb. It's a tight sealed container. It's air and watertight, and so the volume in here is constant, because that's the principle here. Constant volume calorimetry, we have to make sure the volume's constant. So you put the sample you're trying to analyze in here. This is often used for combustion reactions. How much energy is released when a peanut burns, or when this burns or that burns. And so you put the thing you're going to burn in there. There's plenty of oxygen in here. You need a way to start the fire, and so you've got an ignition. And I think that's kind of why it's called a bomb, because it's a lot like setting off a bomb. You know, you give it a charge, but nothing explodes. It's not that fun. So the bomb is in here, and as this burns, it's going to release heat. And the heat is going to leave the little bomb, and the bomb is surrounded by water. The water's going to heat up, and the water is in an insulated container, kind of like a Yeti cooler or something, right? That's not going to let any energy escape. We've got a thermometer in here so that we can measure the temperature change without opening the thing up, because if we open it up, then we're going to let some of the heat out. And we also have a stirrer here because we want to make sure that this water circulates so that the temperature is constant throughout. So when we're measuring the temperature, we're actually measuring the accurate temperature. So here we're treating the calorimeter as the surroundings. And so this is one situation where heat capacity can be useful as opposed to specific heat capacity. The mass of the calorimeter itself doesn't change. because we put the same amount of water in it every time. The mass is constant, and so we can determine the heat capacity of the calorimeter, and then we don't have to multiply by mass. So we've got the calorimeter constant, and we measure its change in temperature. That equals Q for the calorimeter, that's the surroundings, and that's going to equal negative Q for the reaction. At constant volume, Q is equal to delta E. So when 1.55 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole of hexane. The heat capacity of the bomb calorimeter, which was determined in a separate experiment, is 5.73 kilojoules per degree Celsius. Okay, so let's write this stuff down. So we have 1.550 grams of hexane, C6H14. So that's a mass. And then we have the temperature rises from initial temperature 25.87 degrees Celsius. The final temperature is 38.13 degrees Celsius. Notice these temperatures have two decimal places. We're using a better thermometer because here the sig figs in our delta E are going to depend a lot on how precisely we know the temperature, because we're looking at temperature change. So we could calculate change in temperature is the final minus the initial. .13 minus 25.87, 12.26 degrees Celsius. And we're told that the heat capacity for the calorimeter is 5.73 kilojoules per degree Celsius. So delta E for the reaction is equal to Q for the reaction, which is negative Q for the calorimeter. The heat lost by the reaction is gained by the calorimeter. Their signs are opposite. We can calculate Q for the calorimeter. It's the heat capacity, or the calorimeter constant, times the change in temperature. So 5.73, that's not a 7, 73 kilojoules per degree Celsius times 12.26 degrees Celsius. The degrees Celsius cancel out. So this is equal to 70.2498, 3 sig figs. And the unit is kilojoules. E equals Q for the reaction, which is negative Q for the calorimeter. So I found what Q for the calorimeter was, so I'm going to plug that in here. We've got negative 1 times Q for the calorimeter. Negative 1 times 2498 kilojoules, which is just negative 70.2498 kilojoules. They're asking for delta E in kilojoules per mole of hexane. We calculated delta E for this specific amount of hexane. This is for 1.55 grams of hexane. If we want kilojoules per mole, then we need to divide by the moles of hexane. One 1.550 grams of hexane. I'm going to need the molar mass. 6 times 12.01 plus 14 times 1.008. 86.172 grams. So this is 0.0179872 moles of hexane. So we had 70.2 kilojoules of energy released for 0.0179872 moles. I have three significant figures here, minus 3905.5 kilojoules per mole. And when I round that, I could get minus 3910 kilojoules per mole. Or in scientific notation, minus 3.91 times 10 to the third kilojoules per mole. You can't see it? Any questions? Another one? I don't know. I don't remember what's coming next in the slides. So the examples that I'm showing you, which are the ones that the author presents in the book, are showing us that there's subtle differences in how these problems are approached and how they're asked. Just calculating Q here is one thing, but here it's asking for delta E. And we have to recognize, oh, well, because this is constant volume, delta E is Q. And then they want it per mole of hexane, so then we have to find out the moles and divide by that. Negative 3.91 times 10 to the third kilojoules per mole.